here's a summary of what we'll be covering in this project today. We'll start with a brief introduction to the inverse design method. Then we'll be looking at how the mean line design of a Sirocco fan stage can be performed, or a squirrel cage fan as it's called. Then we'll see how the impeller can be designed using the 3D inverse design approach. We'll also briefly look at the design of the volute, and then we'll evaluate the aerodynamic performance of the fan stage based on a CFD analysis. Then we'll be performing a manual redesign of the impeller to improve the stage performance, and then we'll see how the performance of this redesigned fan can be enhanced even further through a redesign of the volute, and finally we'll wrap up with some concluding remarks. So let's start with an introduction to the idea behind the inverse design approach, which we use throughout this presentation. And as you can see in this workflow, these are the inputs that are used by the inverse design method to give us the final blade design. So apart from some basic parameters, these blade loading inputs are really flow related. And so once you have a good understanding of your specific flow issue, whether it's tip leakage or profile loss or flow separation that you're dealing with, it's possible to come up with guidelines on the optimum blade loading to tackle each of these issues. And actually this know-how has generality, which makes it suitable for all your Sirocco fan applications, regardless of your speed or size. And so what's interesting then is that you only need to rely on your knowledge of flow physics, and then this method will work for you regardless of your fan size or which speed number regime it falls under. So this makes the entire process very intuitive and removes any empiricism that is commonly seen with conventional design methods. So in terms of fan applications, we have covered a very wide range, and here are some of the examples that we have worked on. So propeller fans, radiator fans, large-scale ventilation fans, centrifugal fans, motor cooling fans, and this is another motor cooling fan for electric vehicles, so it's a special compact design. And then rotor stator fans for CPUs, a mixed flow axial fan stage for military vehicle cooling applications, and this is a very interesting example of a fan for an avalanche safety backpack, and this was developed together with Arc'teryx. And this is a centrifugal fan for air conditioning, and it's actually a Daikin case study, and also a Sirocco fan on which a paper was published, and which is also the subject of the present work. Now let's look at the design of fans in a bit more detail, and this chart here provides the relationship between the speed coefficient and diameter coefficient as experimentally found by Cordier, and is called Cordier line in the literature. And so across the speed coefficient range, the fans are subject to various flow phenomena and loss mechanisms which are dominant in that particular range. So for example, incidence, losses and flow separation usually take priority when it comes to Sirocco fans, which is the topic of this study. And so the question then is whether it's possible to come up with a set of optimal design guidelines based on these fluid dynamic considerations of reducing the dominant flow losses for your Sirocco fan. And this is actually what we aim to explore through this work.